Welcome everyone. It's top of the hour, Monday, August 16th, 2021. We've got a bunch of great speakers. We have three great speakers for you today over two talks. So first talk will be about quantum machine learning, and second talk will be about distributed machine learning with the Amazon EFS, the Elastic File System Service. So we actually have Senior Product Manager from EFS, and we've got two of my co-workers, colleagues on my same team. So yeah, Antje, do you want to introduce yourself? Say hello.
Sure. Hi, everyone. My name is Antje Barth. I work as Chris as a developer advocate for AI and machine learning at AWS, and I'm co-hosting those monthly meetups with Chris. Thanks for joining us today.
Yeah, and we will introduce Suman in a bit. We do have a lot of material today, so we're going to keep the intros really light, and I think we're just going to hand it right over. So a couple quick links, couple quick updates. So that first link there, let me split them out. That's to all of the community that we've built up here. So that's the YouTube videos and meetups and everything. The second link is a book Antje and I wrote the last year. Here's the duck book, we call it. So if you want to check it out, we do actually cover today's topics in the book. So we cover both quantum and we cover EFS distributed training. But now we actually have the experts here, the ones that built these services, and we want to share that with you. So Raouf, do you want to start and introduce yourself and take it away? You've got about 30 minutes.
Yeah, awesome. Thanks, thanks, Chris. Let me start by sharing my screen.
And just real quick for questions, post the questions right into the chat, into Zoom chat, and we will either answer them or we will ask at the end. And then if there's any lingering questions that we haven't answered, I think we'll leave about 5 minutes for each speaker for Q&A. But we do have to keep moving. We could take anything offline onto our Slack channel. So yes, maybe Antje, if you want to post the Slack channel or maybe later, GitHub repo, you can find off of that link here. I think the respective speakers will post their GitHub repos as they speak, or I'll find them and then post them. So go ahead, Raouf.
Thanks, Chris. Thanks again for the invitation, and I'm really happy to talk to you guys. And hopefully you find this talk useful. So Chris asked me to introduce myself, but also tell you how I ended up doing quantum computing. So it's a natural evolution for me. So as a differential geometry, implement a lot of algorithms in different geometry, and so I was in the intersection between deep math and coding for a while. And this goes back to my PhD work, where I was trying to classify manifolds and partial differential equations based on the geometry they define. One of the things you use to classify is what you call singularities, where things start to be regular, for instance, in the context of PDEs, where the highest derivative vanishes, and so on and so forth. So my first interaction with quantum is in my second postdoc, and when I was looking into Schrödinger equation as one of the PDEs, I tried to understand. Then I discovered quantum computing, and the fact that I can continue doing deep math and code at the same time. And this is exactly what I did, what I'm doing since something I like to call mathematical engineering. So I use deep math for a real application. And I'm currently at QCI, Quantum Computing INC. It's a quantum software company, and I work on trying to make quantum useful. So just to give you an example of the type of math I used and I'm using in the context of quantum computing, so I use algebraic geometry, things like varieties, Grosvenor basis, and so on. For prime factorization, that's probably a familiar topic for you guys, for everyone. And also looked into embedding or compiling inside quantum annealing devices, like Dwave. I also used something called non-commutative geometry. This is stuff like Knuth-Bendix algorithm, writing systems for circuit compilation, which is an interesting topic, a research topic today. And on the theory side of things, I've used algebraic topology to try and understand the speed up in quantum annealing, again, this D-wave stuff, and variational quantum algorithms. I used more abstract mathematics, like topos theory, to, again, understanding where the speed up comes from, but also understanding quantum programming languages. So, yeah, and what is most fun about my job? I guess the fact I'm using deep math to solve real problems. So this is the point of my life where things are coming together, and I see through everything starts making sense now. And also, it turns out, quantum is by itself deep math / physics. So this is the thing I enjoy, and we have to speak the same language as the beast, the quantum machine, to be able to do anything useful. And of course, I have the chance to work with bright people with various backgrounds. So every single day is a new opportunity for me to learn something new. Okay, now the real stuff now, quantum machine learning. So Chris asked me to talk about quantum machine learning APIs. But the thing here, before we go into this, I'll try to give you a simple example. We have to do some mental gymnastics here. The reason is the type of problems we solve or we play with in quantum machine learning are different than the one people are used to in classical machine learning. So I'll give you an example. But I also point you to a very good paper. This is a TensorFlow Quantum. They call it a white paper, but it's a very robust paper, and this is the link for it. So you can find more advanced or more different type of problems. You can use quantum CNNs, but also you can see the use of LSTMs for better initialization of parameters. I'll describe in a moment what I mean by parameters here, and and avoid things like barren plateaus. So,
okay, so Raouf,
yeah.
Yeah, sorry to interrupt. Yes, any way that you could use like a different microphone? It's a little choppy.
Okay, sure.
Sure. And I'll post the link to the quantum machine learning here. Yep.
Can you hear me, guys?
Much better.
Okay, awesome. Okay, so let me start again from the beginning. I was saying, I'll try to give you a simple example today, but the point is the type of problems people are looking into in quantum machine learning are quite different than what you see in classical machine learning. And I was pointing to this particular link here. This is a really good paper for people who are interested into looking deeper into this subject. Okay, so now the key thing here, which is common to all the cases, all the types, all the problems in quantum machine learning is what you do is we train a model, which is a quantum circuit. In the gate circuit, in the gate model, or an Ising Hamiltonian in the case of D-Wave. I'll describe all of this in a moment, but just give you a summary of what I think is the most important thing, or the key thing, is the fact in quantum machine learning we train a circuit, and where intentionally you put the loss function. We take the loss function as the expectation value. And this is you would be surprised actually to know the fact that most of quantum computing today is machine learning, because essentially we have plenty of problems. We have decoherence where it's really hard to maintain the qubits at a given state for a long time, and also you have very small number of qubits. So we try to recycle the qubits as much as you can. And this is where we call variational approaches are very useful. Okay, so let me go to my example. So what I'm trying to do here is training a bunch of rotations to solve an optimization problem. And this is a very easy optimization problem. So we have two variables, x1 and x2. The variables are binary. And in this case, it's not very hard to see. The problem has, the solution is, the minimum solution is at 1 and 1. So this is an easy, of course, this is very easy optimization problem when we solve it by inspection. But you can imagine your favorite optimization problem here. Now, here is the thing. I'll show you how to solve this simple circuit. I'll show you a circuit with two rotations, and I'll show you actually how to train the circuit to solve this this problem using the idea of recycling qubits. So I will start from an initial state while x1 and x2 are pointing to the same direction, 0, 0. And I'll train my circuit, which is again a bunch of rotations, two rotations in this case, to return the correct value. And for the sake of today explaining things, I will do this in using matrices, which is forbidden because matrices are exponentially large. And in reality, we use, of course, circuits, and everything is computed empirically. But let me dig into this. Well, just to give you an idea what a circuit is before switching to matrices. This is the circuit I'm about to train. And, this circuit, however, comes with two particular angles. The two rotations are applied to the two qubits Q0 and Q1, which are initially set to 0, 0. Now, the angles are supposed to be the parameters I'll be training. So instead of having exact values, I'll be using two symbolic variables, θ1 and θ2. And I'll switch to circ here instead of bracket, because circ lets you use symbolic variables. And then when you print your circuit, and this is where I'm defining the circuit, it's not very hard to understand what's going on here. So I'm applying the first rotation with the angle θ1 on the first qubit. This is the first wire or first line here. And I have a rotation by θ2 on the second qubits. So now the game is starting from 0, 0. So these are the two initial directions or values for the qubits. I would like to find the θ1 and θ2 for which I get the solution of my optimization problem. Okay, now I switch to matrices because this is how we understand things. But again, in reality, we don't use matrices because matrices, they blow up very fast. And this is the whole thing behind quantum. So this is a rotation operating on 1 qubit. So people familiar with rotations, they recognize this is indeed a rotation. and it is 2 by 2 because if you have one qubit, then you have a 2-dimensional linear space generated by 2 states 0 and 1. So now we have 2, so we have to compute the tensor product or Kronecker product of 2 matrices, 2 rotations. And when I do so, I get this 4 by 4 matrix. And this is the matrix representation of the circuit. So it's and this is exactly the circuit of the model I'm trying to train. And this is really what I'm doing here. So I mean, there's seems like it's complicated mathematics, but at the end of the day, I'm training this guy here, and by training I mean finding the angles θ1 and θ2 for which this circuit takes me from the initial value of the 2 variables or the 2 qubits x1 and x2 to the solution of my problem. So the trained circuit or the optimal circuit, which comes with the optimal values of θ1 and θ2, takes me from one point of this exponentially large Hilbert space, our search space, to another point with a minimum energy. In fact, what I'm doing here is just training an energy-based and supervised machine learning model. So, so the Hilbert space here, just to continue this example, the Hilbert space here is a 4-dimensional linear space, simply because we have 4 possible values of x1 and x2, these guys here. So in this 4-dimensional representation, the 0, 0, the initial state can be represented by this 4-dimensional vector, where you have 1, where the first coordinate is 1 and 0 everywhere. 1 because this is the stage I'm trying to represent here. So when you apply your circuit to this initial state, we get this guy here. So this is the final state as a function of the parameters, the trainable parameters. Now I'm not done yet because I need a loss function because I need to determine the values of θ1 and θ2 for which I solve the problem. And the way I do this, we don't have to understand it today. I need to map the objective function to an operator or an observable. This is a tiny technicality, and it's completely mechanical. But let me just give you this operator. This is the operator. And using this operator and the final parametric state, this guy here, I have my loss function, and this is the loss function I'm trying to minimize. So again, because this is a simple example, it's not very hard to see the solution. This function is minimized exactly at this point because these 3 terms are positive, and they vanish at this value here. And this is, so if you think about it, this is exactly the right angles because you're starting from 0, 0, and you're applying a rotation by pi over 2. So essentially you're taking the 0 to 1 because the 2 states are orthogonal. So, so we can declare a success, and we have solved our problem or trained our circuit to solve the optimization problem. So a few observations. So the first one is this is a smooth function of the parameters. So you can do all the things you do, all the sorts of things you do when you have a smooth function. For instance, you can apply the gradient descent. And this is, in this case, of course, we don't need to. This is an example, simple example. And again, going back to our circuits, because we're not supposed to work in terms of matrices. We do this empirically, and the way we do it, well, we initialize the angles, θ1 and θ2 to let's say a random value, and then I run the circuit. I take you to the circuit here. So I run this circuit on a quantum computer, and I measure a certain number of times. Let's say 1,000 times, and then I compute the expectation value, the mean expectation value, and then I use this value and update the parameters of the angles using the gradient descent, and I repeat until I see convergence. So this is essentially what's happening. This is when you train this using a quantum computer. Okay, so now I'd like to describe how we do this using TensorFlow Quantum, but expect the same thing for Qiskit and PennyLane and so on and so forth. So the key, I guess the key thing here is what we call parameterized quantum secret as a layer. And where the angles are the trainable variables. So let me just continue my example. I'll show you what I mean here. So remember, this is our secret, and this is the parametric quantum secret. So you feed it with the symbolic, let's call it symbolic parametric secret, and a set of observables. Remember, this is just the objective function written in the language of operators. And so we get to, so we have our layer here, and then you can check with the trainable the parameters or the values of the angles. These are the values of the angles randomly generated or initialized here. Now, to compute the expectation value, I will do so with the TensorFlow Quantum parameterized quantum circuit layer. I will compare it with my exact computation I did before. But to do it, you have to define what we call a quantum data. So in this case, I don't need any data. So this is an empty circuit, and I pass it to my layer. So this is my input layer. Now, if I apply my PQC layer to the input, I get this value here, and this is the expectation value, the empirical expectation value given this circuit and given this objective function. When I compare with my exact calculation, remember this is my expectation value. This is exactly my exact expectation value. I substituted to values of the parameters. I get exactly the same number. So now, so the next thing we do is we package this inside the QRS layer. This is what I'm doing here. So you see here I have two parameters corresponding to two angles. So we are almost done here, but the thing is we have to take into account the noisy and non-deterministic nature of the output the quantum machine returns. And what I'm trying to say here is we got to be careful on the choice of the optimizer we plug into or you compile the model with. This is why people are actually looking into quantum specific optimizers where the gradients are themselves secrets. People are also looking into things like, and of course I'm not doing this here, look into the geometry of the quantum output, very much like Fisher information geometry. And you can do, going back to the initialization of the parameters, you can plug, let's say an STM before the PQC layer and have a better values of the parameters. So this is what you can do But as I said at the beginning of the section, this is very, expect the same thing with PennyLane and Qiskit. So now I'd like to quickly introduce Catalyst, which does exactly the same thing without any background required. So let me just go to my example. So recall this is the function I'm trying to minimize, or this is the function I'm trying to minimize, which is in our context this is the function for which I'm trying to train a circuit to give me the solution of this function here. So there's a tiny mental gymnastic to be done here. So I'm representing this function as a 2 by 2 matrix. This is very common practice when you have what we call a symmetric quadratic function, right? So we can just represent it here by a 2 by 2 matrix, numpy matrix. And you can go back to the symbolic expression by sandwiching this matrix here by x1 and x2. And I get exactly the same value. So this would be my cost function moving forward. So I start by solving my problem using the classical sampler. So the way you do it, you just call the sample cubo on my cubo, and this goes and hits an AWS instance and returns the answer. This is the expected answer. X1 is 1, X2 is 1. Now I can solve this quantum mechanically. So I call the same function here on the same problem. Now using sampler equals brackets simulator. So here I'm using AWS bracket SV1 simulator. This is a particular simulator available. And you run this, you get the same answer as before. This is a tiny little problem. What you can see here, I'm using what we call a hybrid VQE algorithm. This is slightly more complex, a choice of circuits, which comes with an entanglement and more gates than the one I showed you. But you can also run things like QA. Okay, so here's the same example. Now I'm solving this with bracket Dwave, which here I'm changing the paradigm altogether. So what's happening behind the scene is completely different math than the one I showed you today. There's no training involved, but you can solve the problem using the quantum annealing by just setting the sampler to bracket Dwave. I just want to give you one more another example. This is another objective function. Remember, objective functions can be represented as a symmetric matrix. So I'm randomly generating a 10 by 10 symmetric matrix, and I train my circuit, hybrid circuit, using the bracket simulator, and I get an answer here. So yeah, this is very much the end of my technical part of the talk. So I'll finish with trying to answer 2 more questions. One, I'll start with this one here, which is a tricky question in my mind, and but I think one of the things you might expect is a tighter integration of classical machine learning platforms. So, and you're trying to put things together in the bigger context of hybrid quantum classical neural networks, and try to make something useful with this. So I gave you an example very briefly of LSTM side by side with PQC for better initialization of the parameters. So you train faster and you have a better solution. But the thing is, this is actually very, very much dependent on our theoretical understanding of the problems and the type of questions people are raising and asking in quantum machine learning. So there are things which people are working hard to understand and to deal with. Things like barren plateaus or the expressive power of the circuits we consider them. So, and again, I would like to point you to this paper. This is the TensorFlow Quantum paper. So again, so the bottom line is it's very hard to say anything here, but in my mind, these are the two guidelines: tighter integration with classical machine learning platforms, but also very strong progress on the theoretical level. We're trying to understand, the problems and also raise new questions to fully understand the power of quantum machine learning. So this is my last slide. So where to start? So probably if you are a software engineer or data science and machine learning person or computer scientist and not a physicist, you might have a bigger impact here than classic, conventional people with conventional background. The reason is because you come into this with a completely different way of thinking, and this is actually, in my mind, this is an advantage. So, and you can go ahead and try it yourself, which is really amazing. You have 3 machines, quantum machines available on the cloud. You have IonQ, Rigetti, and Dwave, and a bunch of simulators. So go ahead and try them. Start with the most basic thing you can run, and try to make sense of it. Spend time and try to try things and try to again learn by trying. And yeah, here just for fun, I just have few homeworks. If you guys are interested, maybe this is the most interesting one. Again, which I'm pointing to for the third time. This is the TensorFlow Quantum paper. I guess I'm repeating myself here again, but I'm just saying, try to make sense of the things your way, and by trying simple things and moving slowly. Which goes back to my point is, if you have a different background than the conventional background, I think this is an advantage. Okay, so to conclude, I hope the message was clear. Quantum computing today is a lot of machine learning. So this goes back to the fact of the coherence and the fact you have a very small number of qubits that we'd like to recycle. Use the machine again and again and again. So, and everyone is welcome. There's no, again, your new background, your new background might be, it is a good thing. And learning is long because there are a lot of technical stuff here, but so patient, but it's really fun. Because you start to appreciate, the deep mathematics behind quantum mechanics and trying to make sense of quantum mechanics. Okay, this is the end of my talk.
Wow.
Thank you for your time.
Yeah, great stuff. And just based on the chats and, there's still quite a bit of confusion as to what state we're in with quantum machine learning, and yeah, even more broadly with quantum in general. Let me turn on my video here to make this a little bit more engaging. So let me ask one question. I think we probably only have time for one question here. We could take everything else offline on Slack. But what's in 1 or 2 sentences, what is the real potential for quantum machine learning versus classical machine learning? Like, what would be the ideal state? Is it because of the massive parallelism? Is it, yeah, just like 1 or 2 bullet points.
Well, so yeah, this is one thing we expect from the quantum, right? Massive parallelism. So you can do many things at the same time. But also the speed up, you solve things faster, right? So you train your neural network faster, way faster, and also you go after much more complex type of problems. So because the quantum computing comes with much more flexible mathematics, so you can capture new type of problems. But yeah, going back to this is exactly what people expect, going faster, solving problems faster, but also solving very big problems.
Gotcha. So just the scale is beyond anything, or the potential is that we could solve problems. Ones that like pop into my head are, simulating molecules, simulating drugs, things that we have to sort of randomly do today. Where with like classical computers, we can at some point actually simulate and get these low energy states with tons and tons of different degrees of freedom. We can simulate these things at some point in the future and save like hopefully lots of money and discover some new drugs and vaccines and things that we currently do not have. Okay, great stuff, Raouf. Thank you so much for your time. I've reposted the Slack channel for some more follow-up. If you do have time, there's a couple questions, Raouf, about let's see, hands-on intros to hands-on quantum. I did a program this summer. I could share that here in a bit. And I think let's keep moving ahead. So yeah, Ananth, do you want to introduce yourself? And then Suman, don't forget to also introduce yourself. Yes, Ananth, we can't hear you. You're still on mute there. Yep. I can see you talking.
All right. Yes. Okay. All right. I think I'm in now.
Yep.
Yeah. Hi, everyone. So my name is Ananth. I'm a product manager on the Amazon Elastic File System, or EFS, product team. I've been at Amazon and AWS for close to 5 years now. And in my current role at Amazon EFS, my focus is on modern applications and how we can make EFS work better with our container services as well as AWS Lambda, and also working with customers to innovate on AWS. And so I work closely with many of those teams that I mentioned. And so really excited to be talking about how you can run analytics and machine learning inference easily in a cost-optimized way on EFS today.
Sure. Yeah, thanks, Ananth. Hi, everyone. My name is Suman. I'm based out of Bangalore, and I work with the developer relations team. I work as a developer advocate, focusing around machine learning and storage. And prior to AWS, I've been working on most of the storage protocols that we have, like Fiber Channel, Qiskit, and NVMe. And here I predominantly focus on machine learning and its integration with a few of our core storage services. So I'm super excited to share a few of the insights about how you can deploy a machine learning model on EFS at scale. So without any further ado, what we thought to do is we'll run through a demo where I'll show you how you can make use of EFS, which is one of our elastic file system, which you can use to store your data over the network and access that across multiple instances, and how we can make use of EFS on for your machine learning workload. But before we get dive into that, since we have Ananth today, let's first set the stage and try to understand what EFS is, and what just give a overview of for anyone who is new to elastic file system. Ananth.
Yep, sure. So happy to do that. So hi everyone. So I'm back again. So think as the name suggests, EFS is a file system, and it's also an elastic one at that. So what that means is that you can create a file system, and the file system grows and shrinks automatically based on the amount of data you're storing at any given time, right? So you don't have to worry about sizing or scaling your application, and we take care of all of that. And because it's a file system, it's also shared. So which means that you can write data to it and read it not only from an EC2 instance, a container, or a Lambda function, but at scale from those. You can talk about hundreds or thousands of EC2 instances, hundreds and thousands of Lambda function invocations or containers, and so on. And so in summary, it's an elastic shared file system. And by default, it's also a regional service. We also have a one-zone version of that where you can deploy a file system in a single availability zone, and that's at 47% lower cost. But on the regional service, and what happens is every time you write a data to EFS, we persist that data across multiple availability zones, which means it's durable, and we can offer you 4 nines of availability SLA as well. Right. And so if you have an application, let's say your machine learning application or your analytics application either fails over between availability zones or needs to be active across multiple availability zones, you can do that with your EFS file system. And so when we think about EFS, when you think about file system, you typically think about more traditional applications that run on EC2. But since we launched EFS integration with Lambda and containers last year, we're seeing a lot of modern applications. And when I say modern applications, I mean apps that run on containers and serverless that really allow you to iterate and be more agile. We're seeing a lot of applications, customers really taking to using EFS for apps that are running on containers and serverless. And those could be apps that have been modernized from running on EC2, or just net new applications, such as the ones we'll talk about with machine learning inference as well, that run on Lambda as well. And so by using EFS with Lambda, you can really it opens up a whole new set of possibilities and use cases and applications that you really couldn't do before.
Excellent. Yeah. So I guess a few points that you touched upon. One is the scale and the capacity that we get with EFS, and that is something which is predominantly important when it comes to machine learning. So now, when you look at EFS, what would be a good segue into EFS? So why one would need EFS for persistent storage?
Yeah. So basically, there are a few problems that we commonly hear about from customers, and so the key advantages or the key problems, in fact, that we hear are that they want to focus customers want to focus their team's efforts on differentiating work. They don't have time to dedicate to redeveloping already working systems or code. They don't want to be managing their underlying infrastructure, especially data scientists, right? Who tell us that they don't have the skill set to manage underlying infrastructure, nor do they have the desire to be tinkering with stuff that really add no value to their day-to-day job. Right. And so the key advantages of using EFS here are one, that it's elastic and scalable. So your storage automatically scales up and down for the duration of your model, and so or your application. And so if you it's interesting to think about EFS as serverless storage for your serverless analytics application, right? So your compute is now serverless if you're running Lambda, and now you have serverless storage. So your entire infrastructure is completely serverless. It's completely elastic, right? And so what that also means is you only pay for how much you use, right? And so because you put in data, you remove data, you only pay for the amount of data that's in your storage. You don't have to pre-provision your storage or do any of that. And from a performance perspective, it supports the scale in terms of workloads and IOPS and latency as well. And we'll get into that as well, right, as you get into your demo. And finally, also from an integration perspective, it's super simple to use EFS with ECS. It's as easy as just adding it to your ECS task definition. With Lambda, it's as easy as just mounting your file system to a Lambda function, right? It's super simple. And with EKS, for example, with the Elastic Kubernetes Service, we have the EFS CSI driver, which is open source, that you can just use to create the interface between EKS and EFS. So we've made it really easy for you to get started with using EFS. From a use case perspective, common use cases that we see from customers are using EFS for home directories for your apps such as Studio, RStudio, or Tableau. So using home directories for those, running batch jobs using Apache Airflow or AWS Batch, for example. We just recently launched EFS integration with AWS Batch as a source storage. Then we see customers using EFS for data processing and data pipeline. So in case you need to, transform or format your data when you gather them from various sources. And finally, when you if you think about the data analytics pipeline, actually running analytics. So if you're running, let's say, genomics processing or ML inference and so on. So for example, we have an interesting customer is Bayer Crop Science. And so they have, their unmanned aerial vehicles, which collect satellite imagery and sensor data from hundreds of sources on their crops, on crop science, on crops. And so they get all of that data, push it into EFS, and then run insights that enable smart farming and crop management. And then they synthesize all of the data and they share it again from EFS to third parties, right? So that's one use case. Another interesting use case is Asurion, which uses EFS for machine learning. And so what they do is they use EFS for sentiment analysis. So when customers call in to their contact centers, especially during peak hours, as soon as the call gets over, they run machine learning inference on the call to understand what the customer sentiment is, and then they perform follow-up actions, right? And so they use EFS because EFS can scale depending on the peak hours. If you have tens of thousands of people calling in, they can quickly run those machine learning inference models, right? And so those are some interesting use cases there, I would say. And one of the reasons why EFS shines there is, especially for Lambda, you need to have shared data that can be used between various Lambda invocations, right? And so typically you've been constrained by the temporary storage that Lambda has, but with EFS you now have access to almost petabyte level storage that you previously couldn't have. And so with ML inference use cases, the first thing you want to do is to have a shared set of libraries on your Lambda invocations, right? So this could be MXNet, TensorFlow, or something like that. And then you have a shared model file, and the model file is where that you're running your inference of, right? And so this could be, again, like I said, sentiment analysis, image classification, all those kind of stuff. And so every time your Lambda function gets called, invocations spin up, and then they run the model, and then you get results, right? And so EFS is really fast. It provides really low latency there, and it's elastic, right? And so it's really a great use case for analytics and machine learning inference, I'd say.
Exactly, right. Yeah, sure. So I guess we got one of the questions that, if you can spend some more time on describing the integration of EFS with Lambda. And that is exactly what we are going to show in the demo in a bit. So if you have any further questions, feel free to put that in the chat. We will, we'll be happy to answer that. So Ananth, before we jump into the demo, one last thing would be, this is pretty common across AWS in many of the services, as we have a lot of different services around storage. And when we think about S3, EBS, and EFS, now, when should customers select EFS over EBS or S3? Can you share some lights on that?
Yeah, sure. So that's a great question. So let's start with EBS, and then we can get to S3. So with EBS, the main consideration with EFS is that it's a single attached block storage device, service, right? So it works well for use cases where you have storage that's specific to a specific instance of an application, such as a container or an EC2 instance. But if you want to share data between multiple resources, you need a shared file system, and that's where EFS kind of comes into the picture. Another reason is the regional nature of EFS, right? That I just talked about. If your application wants to fail over from one AZ to another or operate across multiple AZs, EFS is a good option. From a performance perspective, there's typically throughput, IOPS, and latency. Between throughput and IOPS, they're fairly comparable between EBS and EFS. They're both comparable and configurable, I would say. The only difference is between EBS and EFS from a performance perspective is with latency, right? And latency is a simple way of defining latency is how long does it take for an operation to return from storage, right? And so there are some latency differences just because of the way that the services are built. And for example, EBS is all your data is within a single availability zone, whereas with EFS, as I mentioned, we write it to multiple availability zones, right, for durability purposes. And so there are more transactions that happen behind the scenes. And so EFS gives you low single-digit millisecond latency, while EBS provides sub-millisecond latency for operations. And so for in most cases, it really doesn't matter if you're reading and writing big files, you aren't going to notice that difference. But there are some use cases where you're doing very frequent transactions with small IO. That's when EBS is really a good fit. All right, so that's EBS. Let's talk about S3 now. So a lot of these properties are also similar to S3. So S3, read the regional nature and the shared nature. But the two big differences from about when you would use S3 or EFS are what I would call file and access patterns. And so by file or API, I mean if your application already uses files, reads, seek, writes files, closes files, and so on, right? So typical file stuff. Using EFS is usually much easier than rewriting your application to use an object interface, right? And so it really makes sense to have a file interface instead of an object interface within your Lambda function, for example. The next thing is access pattern. So if you with S3, if you have to download or import your files or your ML model every time, right? You also have to build in logic to see whether the object on S3 has not changed, for example. Within EFS, all of this is natively available because it works with files and it understands all of this. And it also provides caching under the hood. So for example, with Lambda, if you use an existing container, you don't have a cold start problem with EFS because the data you access would probably be instantaneous because it's not necessarily reading over the network every time, right? So the first time you might, as with Lambda, you might have a cold start, and then subsequently the file is stored within the cache, right? And so and finally, the last thing is if you're constantly reading files, then you don't have to pay for read or writes on EFS. You only pay for the underlying storage, right? So it also depends on terms of the read or write access patterns that you have on EFS. So hope that helped.
Yeah, right. Absolutely. So I guess we just got one more question. If you can spend maybe 30 seconds on this, because it's an important question. So Jack asked, can you compare Lustre FS versus EFS? If you want to give a few pointers on that before we jump into the demo.
Yeah, so FSX for Lustre is great for applications that use significantly high level of that need significantly high compute power, right? So we are talking about applications, that require very high simulations, for example. So if you're doing some sort of VDI application or electronic design sort of applications that really require significantly high levels of compute. So those are the sort of applications that are a great fit for FSX to Lustre.
Excellent. Sure. Thank you so much, Ananth, for all the brief about EFS, and I hope that was useful. And for others, if you have any questions, feel free to put that in the chat. And while I show the demo, maybe Ananth can answer a few of your questions.
Yep.
Okay. So with that, let me jump into the demo. So for that, I need to share my screen. So let me do that. Okay. So I hope my screen is visible. Okay, All right, so what we are going to do is in next 20 minutes is we are going to show you how you can deploy multiple machine learning models using AWS Lambda and Amazon EFS. So before we get started, I'll be sharing you all the code. If you want to experiment with that, play around with that in your account, feel free to do that. And also we are probably coming up with a blog post which will be around this where we will spend a lot of things, we'll spend more time on all these components, which we are going to show you now in much more details. But I just want to give you a sneak peek of what are the capabilities of Lambda and EFS when it comes to machine learning inference. So to start off with, what we are going to do now is we are going to solve one problem, and the problem is let's say you are a machine learning engineer or data scientist, and you have already built a model which can extract text out of an image. Okay, so this is the model that you have already trained and built. Now, what we want to do is we want to deploy that model in a serverless fashion. So as Ananth mentioned, EFS is also, you can think of it as a serverless offering from the storage standpoint, because it scales automatically. It doesn't get provisioned immediately. So it's based on your usage, it will scale. So what we are going to do is we are going to deploy our model on the cloud that's on AWS, and we are going to see what are the services that we are going to use within this AWS icon that we have shown here. But ultimately what we expect is it will do the inference on your ML model which you have trained, and it will give the prediction as the text in that image. Okay, so we are going to use easy OCR for this ML model, but you can replace that with any model. So you might have trained this model on SageMaker, or you have trained this model natively within an EC2 instance, whatever it is. We are talking about the deployment part, okay, not during the training part. So if you look at this whole architecture, so this is what the architecture would look like. Okay, so before we go to the details of this architecture, I want to show you how it would look like. So this is the inference that we are going to do, and I'm in Postman, and this is the endpoint of our application, and this endpoint is nothing but this API gateway. Okay, so all we want after the whole deployment is this endpoint, okay, which is in Amazon API gateway. Now, if we send a post request with the URL of the image, okay, this is the image URL, and if I just send this, what I expect is it is going to do the inference in your machine learning model. And for our case, the machine learning model we have is an EC OCR based model, and it will predict like this, right? So it will correctly predicted the text in this. So if you want to check that, we can copy this URL and check it in our browser maybe, and we'll just see this is the exact same text that we got from our prediction, right? So this whole execution that has happened after I clicked on this post request and getting this inference, everything has happened in a serverless fashion. There is no server which has deployed this model. There is no server which has this a model stored. So everything is in the serverless fashion. Now, when you look at this whole application, how we have deployed it, it's like this. Okay, so I'll break it down into two parts. The first application is when you as a machine learning engineer, you're done with the training, and what you do is you will push the model into an S3 bucket. Okay, and if you are, let's say, if you are training this model using SageMaker, so the model artifacts will be saved in Amazon S3. So you don't have to push it. So it would automatically be there in S3. Now, the moment a new model comes in S3, it will trigger a Lambda function. And that Lambda function, what it would do is it will just copy that model artifacts or the .pt file from S3 to EFS storage. Right. And once this is in your EFS storage, now you can do the inference. Right. So imagine that you are building a model for text for this particular use case. Let's say you are building a model for extracting text from an image. So obviously you will be training your model for different languages. So let's say today you have a language support for 3 languages, and tomorrow you have trained your model with a new language support. So all you have to do is you just have to train that model, and once the training is done, that new model artifacts will be saved in S3, and that would automatically go to EFS. So you don't have to manually push your model artifacts to EFS. Now, once that is done, what we can do is we can do the inference. And for this inference, we have another application which contains 2 services. One is Amazon API Gateway and AWS Lambda. Now, what this Lambda function is going to do is this will have the business logic, and the business logic is very simple. It will take the request through the API gateway from the client, that is the user, and it will send that URL to this Lambda function. And what this Lambda function would do is it would simply use the model which is saved in this EFS storage, and it will do the inference from there. And once it completes the inference, it will send the prediction back to the client, right? So as you can see, we could have done the inference directly from S3, but as Ananth mentioned, that may not be the right choice in this case, because over a period of time, when you do a lot of inferences, you will be you want this inference to be cost effective, right? So when you do through S3, you will be spending money on every API calls that you send, because it's at the end of the day, it's an API call to S3. Whereas when the model is saved natively in EFS, it is locally accessed by the Lambda instance, right? Because it's a native file system. It's it's a network file system, and you can access it any number of times. So you won't be charged on that. So that's about this whole architecture. So now what we are going to do is I'm going to show you, this app 1 and this app 2, both of them, and what is the logic and how we are threading this together. Now, I'm not going to show you, how we have deployed this, because we have used a framework called SAM, which is a serverless application model, which is one of the framework that we have to deploy any serverless application. I will share the code with you, but if you are interested, you may like to, deploy this using SAM or any of the, other framework of your choice, or you can do it manually as well if you are playing around with this. So now what we are going to do is I'm going to show you the code. So this is my project folder, and I've used SAM for this. And when you do SAM, the first thing that you do is you do SAM init. Okay, and once you do SAM init, it creates a project folder, and inside that you automatically get some boiler code and all of that. But we are going to see that later, because deployment is not important at this point in time. But if you look at Lambda functions, I have deployed this whole code using SAM from here. I have not used UI, but I want to show you the Lambda function which it internally creates, right? So if you remember, we have 2 functions, right? 2 applications, app 1 and app 2. So let's first get into this app 1, whose sole job is to trigger and Lambda function, which will push the model from S3 to EFS. Now, if you see here, we have this Lambda function called ML model upload function. And if you see the code, it's pretty straightforward. Let me just adjust the screen. Yeah, so it is a very straightforward. I guess here it's little small, so I'll just open it here. So I'll go to my project folder, and I'll go to this S3 EFS folder, and we have app.py. Now in this code, in this few lines of code, it's pretty straightforward. We have a Lambda function, and it takes an event and the context, the standard 2 parameters that the Lambda function expects. And this event will be triggered on an object upload on S3, right? And the moment it sees an object, and in this case, the object is nothing but the ML model. or the ML model artifacts. What we need to do is we need to capture the bucket name and the key, that is the file name or the model name or the .pth file. And we just have to simply download that file in this Lambda, within this Lambda instance. But we are not going to, if you see here, we are not downloading it in the local file system of this container where this Lambda is will be running. We are saving this into our EFS file system, and this is the EFS file system mount point. Okay, and how this EFS file system is mounted on this Lambda instance, and that is something we have mentioned in our deployment template. Here what we call it as a SAM template. If you see here, template.yaml file, there we have mentioned that for this Lambda function, which EFS file system should be mounted and what should be the mount point. Okay, I'll walk you through this template in a while, in a couple of minutes from now. But this is the location where the EFS file system is mounted. Okay, so this is about the first application. It takes the object or the model on from S3, and it just downloads it, not on the local file system of the Lambda instance, but on this EFS file system. Okay, so we are done with this part, right? So now let's look into this, ML inference, which is the which is more interesting from this application standpoint. So if you see here, we have another folder called ML inference, and inside that as well, we will have one app.py file. So let me just open this file, and I'll quickly walk you through this file, this code. So here we are just again mentioning the mount point, because this Lambda function also need to access the EFS file system, right? So if you again go look at this architecture, this Lambda function should have the access to EFS storage, and that's why we need to have the mount point. Similarly, in the previous code, we have seen that this Lambda function also needed to have this access to EFS storage, right? And this is the beauty of EFS storage. You can share it across multiple Lambda functions, containers, and EC2 instances, and so on. So it's pretty flexible. So now the thing that the objective here is very simple. This Lambda function should be triggered when through an API gateway, right? So if you look at this Lambda function will be triggered whenever there is a request, coming from the client on this API gateway, right? And what we have to do is we have to read that data that the client is sending. In this case, the data is nothing but a URL, which we have seen just a while back, and we have to just send that URL to the model, right? So that's all. That's the only job of this Lambda function. So what we are doing here is we are just reading the body from this event body hash, and once that is done, all we are using is we are using easy OCR. If you see in the in the line number 2, this is the package that this is the library that we are using for this. And if you want to look into that, it's a beautiful library for extracting text from an image. I guess it is written in PyTorch, and it uses VGG network. So it's a pretty nice library to look for. So if you're new to CNN or deep learning, you may like to spend some time on this. It's a beautiful package. So all we are doing here is we are calling this reader method, our reader function, and we are sending the language list. So if you look at the inference, you might have seen that we are sending two things to our Lambda function. One is the URL, and another is the language, right? So because we should know what language the text is present in this image, right? So whatever is the language, we have to just put that using a comma, right? So if it might so happen an image contains a text with a couple of different languages, right? Maybe English, French, and so on and so forth. So we just have to send all those languages, in the language hash. So what we are doing is we are just reading that model from our EFS storage, right? So this is the model dir, and again, this model dir is nothing but our EFS file system. It's not coming from the local storage from where the Lambda is running, right? Because it is not persistent. We know that it will the whole infrastructure in the backend will go off when we run Lambda, right? So once that is done, what we are doing here is we are just sending the URL to this method called a read text, right? So it's actually a 2-line of code, this line number 23 and line number 25. Okay, and once we do this inference, because this is the place where we are doing the inference, and this inference is going to your EFS storage, right? And one of the reasons that why we have this if condition is just to optimize the performance a little bit, because let's say if I send another URL, another image, but this time maybe the image contains only English language text. In that case, what we want is if it is going to the same Lambda instance, we want to optimize the performance a little bit. So what we are doing here is we are caching it for any unknown language which it has, it has done the inference in the recent past in this model cache, dictionary, so that it doesn't have to go back for fetching the model again, right? So this is just a little bit of cost and performance optimization. Okay, nothing much. So once that is done, what we are doing is we are just formatting the response, and we are just dumping it and returning it to the a user, and we are also printing it into our logs as well, just for troubleshooting. So that's the whole thing about this application. Now, if I quickly go over the template. So this is the template which we have used. This is a SAM template which you can use to deploy this whole application without going into the UI or using any CLI and all of that. So I will not go deep dive into this, but what I want to show you is two resources, that is these two resources. So these two are the resources which creates the Lambda function. One is the ML model upload function, and another is the inference function. And if you remember, these are the two functions. If I just go back here to this function, if you see this, these are the same two names, right? ML model upload function and inference function, right? And then there is some random text just to have a uniqueness in the name, right? Because it's automatically generated. So if you see here, we have in both these functions, we have attached the EFS file system, and we have mentioned where it should mount locally, right? So it should mount in MNT ML, right? This is the mount point which we are mentioning for this particular Lambda function, right? Similarly, in this Lambda function also, if you come down, you will see that local mount point, right? And we know that this location is needed, and within the Lambda function, if you go up in the global parameter, we have these two environmental variables. And since we have mentioned these two environmental variables, we could run this, use this os.getEnv method to fetch the environmental the mount point, right? So if you want to change the mount point, you don't have to change this code. All you have to do is you have to come here and change the mount point in this place, right? And you can make you can just redeploy this application. So that's about it. And these are the two resources that we have created, two functions. And above this, all of these, what you see here is because of EFS, because we need to create an EFS file system as well. And for that, we need to create, we need to have access to this EFS file system, from outside. So that's why we have created, different networking resources like Internet Gateway, NAT Gateway, and all of that. So that's not that important at this point in time. But if you want to try it out, feel free to make use of this code. Now when you start off this project, if you want to do it in your environment, what we have to do is I'm going to share you these two folders of code, whatever code that we have seen, right? Within this S3 EFS and ML inference folder, where you will get the code for both the applications. What you have to do is you have to first run a SAM init. Okay, so this will instantiate your SAM project. And once that is done, it will ask you a few basic questions. I guess I have the screenshot for this. Yeah. So if you do SAM init, it will ask you for a few basic questions, and you can select, based on your requirement. So the blog that we are coming up with, it will contain all this information, but I just want to show you, how this whole SAM thing works. So once this SAM init is done, all you have to do is you have to go to the project folder. Okay, so once you do the SAM init, it will ask you for a project name, and I have given the project name as my ML project, and that's how it created this folder. If you see here on this left hand side, right? So you have to go to your project name, whatever you give the project name. Okay, so once you do that, the next thing you have to do is you have to edit the code. Okay, you have to edit, you write your application code, you have to change this YAML file and all of that, right? And once this is done, what you have to do is simply run SAM build. Okay, so this will build your application, before you deploy it. And once that is done, finally, you just have to run SAM deploy. Okay, so once this is done, or once this SAM deploy command is done, you will see all the resources that you have mentioned in this, YAML template. Every resources will get deployed on your AWS account. Okay, and when you run it for the first time, you have to use -G option, which will again ask you a few questions regarding the inference. Not inference, sorry, regarding your application. Like if you see here, when I ran this SAM -G guided or -G, it asked me about the project application name, and it also asked me about the S3 bucket, right? So because if you remember, we have created two Lambda function, and one of the Lambda function should get triggered when there is an upload of the model in your S3 bucket. So this is the place where you mention which S3 bucket. Okay, so this is the S3 bucket which you should have in your account. If you don't have, you can create one and give the right name here. And then you just have to, these are the few of the details which, I will share in the GitHub repo so that you get better context around this. So that's all about it. And the last thing I want to show you is the EFS file system, what you if you want to see from the UI. So you can go to any of these Lambda functions. So let's say, because EFS is attached to both the Lambda function. If you come to configuration, and if you click on file system, you will see a file system here, right? And if you click on this file system, you will see that this file system got created, automatically using that SAM template. And you can see that what is the storage it is using, what is the capacity it has, and all of that, right? And one important thing is, if you click on VPC, you will find VPC, information here. Now, if you're not new to Lambda, if you simply create a Lambda function is not created within your VPC, right? So it gets created within the AWS Lambda VPC, and you get, you access your Lambda function. But why we need VPC? Because we are using EFS file system. Because when you create EFS file system, you can create the file system only within your VPC. Right, and now to access that VPC, your Lambda function should also be part of that same VPC. So that is the reason when you look at this code, you see, all these network resources that we wanted to create. All right, so for this particular deployment. Right, so that's about it, and I'm going to share you this GitHub repo, and there is some changes that I've done just before this demo, so I'll push that now, and maybe at later point in time, once we once we publish that blog, we will append that in the YouTube link as well. I'll request Chris to update that at later point in time. So yeah, that's about it. If you have any questions, feel free to connect with me via LinkedIn or the Slack channel, wherever you feel like, and we'll be happy to answer your questions. Back to you, Chris.
Great. Great stuff, Suman. Okay, we have actually, since we're already a little bit over, let me ask just one question here. Where'd it go? It was a good question. So this question about the cache, but I think we got that. Okay, Sam, actually, I think we answered pretty much everything. There was kind of a, yes, Suman, go ahead.
I'm sorry. So I'm just reading through the question. So I think Jack asked a right question. Where is there any Docker definition for the second Lambda function? That's exactly correct. We do have a Docker definition for that, and I'll share that with you in the code. You can refer to that in the GitHub repo as well. Yeah. Yeah. Go ahead, Chris. I'm sorry.
Yeah, great. And is the code available? Did you say, or that's coming with the blog post?
Yes, the blog post will have all the details, but the code is available. This is the link, and what I'm going to do is I'm going to put the README file tomorrow, and I'll push the updated version of the code after this session. Yeah.
Great. Excellent. I think that's it, everyone. Thank you so much for hanging in there. Yeah, we actually retained quite a lot of people for the past hour 20. So appreciate it. I'll post this as soon as the video becomes available from Zoom. I'll download it, clean it up a little bit, and then re-upload it to this location that I'll put here, youtube.datascience on aws.com. So that's it for this month. Antje, you're here, right? What do we have going on next month?
Yes, we do already have the agenda published, I think, for next month. So let me just make sure, going there as well. We do have, do you got it? Hierarchical forecasting with Qiskit HTS and recommendation engine so far. So
right,
we'll make sure.
Engines,
yeah,
SageMaker, and that's
correct.
That's from Keisha from
yeah,
the A Cloud Guru. Awesome, she's a great speaker. We've had her on the show before, and super excited. And then we've got Manny, who we've also had on, and Farouk. We'll be talking about hierarchical time series. So we don't have a whole lot of time series on this webinar meetup, so I'm pretty excited to get some of the experts in that are actually working with time series models using Prophet and SageMaker. Prophet comes out of Facebook, and they can walk us through, and we'll certainly provide demos and samples for you to take home. So thanks, everyone. We'll see you next month. Bye-bye.